Hi friends, so in this session we are going to see the multiple choice questions on damped and forced vibration. See, in last session we have completed with the introduction to vibration and undamped vibrations. Now we move to the next point. So I have taken the multiple choice questions on damped vibration and forced vibration. On the front page, whatever the multiple choice questions which are available, which are of the damped vibration. So we will start to solve. The first question, just read the advantage of critical damping. So before going to that, I want to show one graph. Suppose if I plot displacement with respect to time for damped vibration, then this graph will be of undamped vibration. This is of undamped. Then this will be for critically damped, and this will be for over damped. See, these concepts I have already explained in my earlier videos. So if you want, then you can visit that video. So I have given the three damping with displacement with respect to time on this graph. So here you can see there is a vibration with damped vibration, means the particle will move up, down, so that cycle you can observe. For critically damped, it will move, displace from equilibrium position, and again it will come to the equilibrium position, means it will not move in the opposite direction, means it will come with short time to the equilibrium position. And in over damping system, if I displace the particle, then because of the over damping, it will take a long time. So it is the sluggish. So it will take long time to come to equilibrium position, and it will not cross this equilibrium position. It will means the energy will not convert it into the other form. Okay. So there is a displacement, means it will move from the equilibrium position, and it will come to equilibrium position without vibration, but the time which will require will be more. म्हणजेच काय बघा बाळांनो, की अनडॅम्प्ड व्हायब्रेशन मध्ये व्हायब्रेशन होणार, म्हणजे बॉडी इक्विलिब्रियम पोझिशनच्या अबाउट मूव्ह राहणार. क्रिटिकली डॅम्प्ड ओव्हर डॅम्प मध्ये बॉडी मूव्ह होईल, इट विल मूव्ह टू द पोझिशन बट it will come to equilibrium. But for critical damped system it will take less time, and for over damped system it will require more time. Okay, now just read out this statement. The advantage of the critical damping is the vibratory body comes to rest in smallest possible time. There is no vibration. The amplitude of vibration is maximum. The amplitude of vibration is minimum. See, here the body comes to rest with minimum time. Okay, so the answer is the vibratory body comes to rest in smallest possible time. Now next, the underdamped vibrating system, if x1 and x2 are successive values. मी इथं दाखवते बघा, just see, suppose this is the first amplitude x1, suppose this is the second amplitude x2 in the underdamped system. Then on the same side of the mean position, then the logarithmic decrement. See, I have in earlier videos I have explained the logarithmic decrement and how to derive the formula. That formula is delta is nothing but equal to log to the base e. It is the ratio of successive amplitudes, that is x1 by x2. So this is the formula for logarithmic decrement. So just see the formula. So it is log to the base e. This is the log x1 by x2. So answer is C. So natural log of x1 by x2 is the logarithmic decrement. Okay. Now next, a system is said to be critically damped if damping factor for the system. Now first we'll see what is the damping factor. Damping factor is nothing but damping coefficient divided by critical damping coefficient. This is the ratio which gives the value of zeta, and zeta is nothing but the damping factor or damping ratio. When zeta is less than 1, then that system is underdamped. When zeta is equal to 1, that system is critically damped, and when the zeta is greater than 1, then system is overdamped. Okay, now just read the statement. When the system is critically damped means in the damping your damping factor C is equal to Cc. Okay, so when this C will become equal to Cc means zeta will become equal to 1, means for the critically damped system the value of zeta is nothing but 1, so it must be equal to 1. So damping factor is equal to 1, so the answer is B. Now next, the amount of damping necessary for a system to be critically damped. आत्ताच आपण बघितले बघा, here what we have seen, the C value must be equal to critically damping. So when C is equal to critical damping coefficient, then the value of zeta will become 1. So C should be equal to Cc. So the amount of damping should be equal to critically damping coefficient. So C should be equal to Cc. Now next statement, the ratio of actual damping coefficient to critical damping coefficient. हा इथं आताच दाखवलाय बघा. The ratio of actual damping, that is C, divided by critical damping Cc is nothing but zeta, and zeta is damping factor or damping ratio. So it is damping factor. Okay. So the last 3 questions are based on C, Cc and zeta. Now next question. In a light or underdamped vibrating system, means here they have considered zeta is less than 1, so the system is underdamped. Okay, the natural logarithmic of the ratio of any two successive amplitudes is known as, see, natural log of successive two amplitudes. So this is the formula of delta, and delta means it is the logarithmic decrement. So the statement is given of logarithmic decrement. So the answer is logarithmic decrement. Okay, D. Now next, a system is said to be overdamped if damping factor is, see, in first graph we have seen that for overdamping system the value of zeta which is required, that should be greater than 1. So the answer of this question is a system is said to be overdamped if damping factor is greater than 1. So it is to more than 1. So answer is A. Okay. Now next, just read out the statement 8. An overdamped system is disturbed from the equilibrium position with some initial velocity. The system will, now again we'll go here, see, here I have displaced this system with overdamped. We have to consider this third graph. Okay, this one. So it is displaced. After displacing, see, it will come to equilibrium position, but it will not cross this line. Means it will not go on the lower side. Means there is no vibration. So it will displace and again come back to its initial position. So it will not cross the equilibrium position. So the answer is A. It will not cross the equilibrium position. Okay. If you read the B, C, D, then you will get the B is vibrate about the equilibrium position. There is no vibration. It will displace and come to equilibrium. The C is immediately return to equilibrium position. No. In critical damp, it will immediately come to equilibrium position. In overdamped system, it is actually a sluggish response, so it will take a longer time. Okay. So the answer is A. Now next. Okay, now read the first statement. During resonance, see, in last session, means the first lecture on multiple choice questions, there I have given the definition of resonance. I am going to repeat again. The resonance means the external excitation force which is applied on the system, its frequency should match with the natural frequency of the system. ही काय सांगते बघा, रेझोनन्स म्हणजे काय, तुम्ही बाहेरून जो फोर्स लावलाय त्याची फ्रिक्वेन्सी आणि बॉडीची फ्रिक्वेन्सी ही काय असायला पाहिजे, सेम. So when there is the same frequency of external excitation and body, then that concept is called resonance. आता resonance मुळे काय होणार आहे? What is going to happen because of the resonance? Because of the resonance, amplitude of vibration is going to increase and increase till the failure. So now read the statement. During resonance, high amplitude of vibration, low amplitude of vibration, no vibration, vibration remains unaffected. काय होणार आहे बाबा इथं? Due to resonance, the amplitude is going to increase. So you will see the high amplitude of vibration. Okay. The next question. The speed at which resonance occurs is called. Now the speed at which resonance occurs is called critical speed. It is called critical speed. Means we'll have to achieve such speed that there will be resonance. Means we'll have to reach to the natural frequency of the system. Okay. And this same critical speed is also called as whirling speed. Its third name is whipping speed. So all these terms whatever I am talking are same. म्हणजेच क्रिटिकल स्पीडलाच व्हर्लिंग स्पीड म्हणतात आणि व्हर्लिंग स्पीडलाच व्हिपिंग स्पीड म्हणतात. सो यू विल गेट नंबर ऑफ ऑप्शन्स इन दॅट देअर शुड बी ह्या तिघांपैकी काय असलं पाहिजे? वन ऑप्शन. ओके. द स्पीड ॲट विच द रेझोनन्स ऑकर्स इज कॉल्ड क्रिटिकल स्पीड. ओके. नाउ नेक्स्ट. The factor which affects the critical speed of the shaft is. Now for that you will have to see the critical speed. In the critical speed, with the shaft rotation, the centrifugal force will act on this shaft. Suppose this is my shaft and this is the body which is rotating, supported on the bearings. Now suppose the centrifugal force because of the rotation m omega square is acting on this body, this will be deflected. Means its equilibrium position will change by distance e. So that depends upon the diameter, that depends upon the displacement, that is the eccentricity, okay, and the length of span. Means the critical speed will depend upon eccentricity, diameter, span, means all of above. So critical speed will depend upon all of above. Now the angle between spring force and damping force. Yes, I am going to explain this term. See, if you want, then you can refer any book. In that any book, actually for forced vibration, the derivation is given with respect to its differential equation, and that differential equation having number of terms, and that terms I am going to explain. See, in normal any differential equation there is spring force, there is inertia force, and there is damping force. And if I plot the graph of that differential equation, that graph is, मी तो plot करते बघा बाळांनो. This is the K, you can say X or A, C omega A, this is m omega square A, and this is the force applied. So this is the graph, and with horizontal, if I consider this angle, then this angle is, this total angle is omega t, and this angle is phi. Okay. So that differential equation you can represent in graphical form. And if you know this graphical form, then you can give these answers. Now just read the statement. The angle between spring force and damping force. See, this kx is the spring force, and c omega a, c means damping coefficient, so this must be a damping force. त्यांच्यामधला angle किती आहे बघा? This angle is 90. Okay, so the answer is 90. Okay, so if you know this graph, then you can easily write the answer for these questions. Okay, so this is the graph which is plotted from the differential equation. Okay, now the angle between inertia force and spring force. See, this kx is inertia force and its direction is towards we can say right, and m omega square x is nothing but the inertia force. Okay, so spring force and this is the inertia force. Both the forces are parallel and unlike means directions are opposite, means if you take the angle between these two, if I plot on same line, then the angle between two will be the 180 degree. So the angle between inertia force and spring force is 180 degree. Okay, so the answer is B. Okay, for these two questions you will require this graph, okay, which is plotted from the differential equation for force vibration. Okay, now the next two questions, that is 6 and 7, they are from unit 5, but unit 5 is based on unit 2. So in this book they have included this question number 6 and 7 here, that is the unit 5 questions. So vibrometer is designed with low frequency and accelerometer is designed with high frequency. Now I am going to give the difference. See, in vibrometer we measure the amplitude. So to measure the amplitude, your system should have low frequency, so that you will get the maximum displacement. And in accelerometer, to get or to measure the acceleration, your system should have high frequency, so that whatever the displacement you are going to get, that will be proportional to the acceleration. Okay, so just keep in mind that vibrometers means the amplitude measuring seismometers are having low frequency, and acceleration measuring seismometers are having high frequency. Here displacement measuring seismometers are having low frequency. Vibrometer means displacement measuring seismometer, and accelerometer means acceleration measuring seismometer. Okay, so just keep in mind, in vibrometer we measure the displacement, so it should have low frequency. Here we measure the acceleration, so it should have high frequency. Okay, now next, the 8th question. Just read the statement. The ratio of maximum displacement of forced vibration to the deflection due to static force is known as. See, for that I am going to write amplitude of vibration for forced vibration. Amplitude, okay, for forced vibration, it is given by x is equal to amplitude of vibration, x is equal to f naught by k divided by root 1 minus omega by omega n square whole bracket square plus 2 zeta omega by omega n bracket square. Okay, now what is the stiffness? The stiffness K is nothing but force divided by displacement. So from this you can write displacement should be equal to force divided by K. So here you have F naught divided by K. F naught is the static force applied, means the inertia maximum force applied on any vibrating body. So this will provide you the value of x. So I can replace this as x, but for the static condition x st divided by this root 1 minus omega by omega n bracket square whole bracket square plus 2 zeta omega by omega n bracket square. Now transfer this x xt on this side, so this will become x by x st, and here instead of x st here will be 1. Now the ratio of this x by x xt is normally we call as magnification factor. We call it as magnification factor. Now read the statement. The ratio of maximum displacement of force vibration to deflection due to static force. See, this is the maximum deflection of force vibration. This is the deflection due to static force. So x by xst ratio is nothing but the magnification factor. So the answer is D, that is magnification factor. Okay, so the answer is D. Now next, in a vibration isolation system, if omega by omega is greater than 1, the phase difference between transmitted force and the disturbing force is. See, in any vibration isolation system, if omega by omega n is less than 1, then the phase difference is 0, and if omega by omega n greater than 1, then its phase difference is 180. So the answer is 180. So in vibration isolation, if omega by omega n is less than 1, then phase difference is 0, and if it is greater than 1, then its phase difference is 180. So we have to keep in mind these things. Okay, next, 10th, just read the statement for the 10th. In vibration isolation, if omega by omega n is less than root 2, then all values of damping factor, the transmissibility will be. Now see, I am going to write the formula for transmissibility first. The transmissibility, it may be force, it may be displacement, it is given by, I will write the formula first. The transmissibility formula, how to remember, I have given how to remember in earlier videos. Just see, you have to write the formula of x, means denominator of x. This denominator is 1 minus omega by omega n bracket square whole bracket square plus 2 zeta omega by omega n bracket square. Here you have to make this first term as 1 and keep second term as it is. So this is the formula for transmissibility. Transmissibility means in any vibrating system, the vibrating system will transmit the force or displacement to support. So how much amount of force or displacement is transmitted to that support, that we calculate by using this formula. कळलं तुम्हाला या फॉर्म्युलावरून काय मिळणार आहे आपल्याला, फोर्स सपोर्टला किती ट्रान्समिट झाला किंवा डिस्प्लेसमेंट सपोर्टला किती ट्रान्समिट झाली, that value we are going to get by using this transmissibility. Okay, now here suppose if I consider TR is equal to 1, or they have given the value of omega by omega n is root 2. So I will put the omega by omega n root 2 here. So just calculate 1 plus 2 zeta root 2 bracket square divided by 1 minus root 2 square bracket square plus 2 zeta root 2 bracket square. Okay, so I have just entered the value of omega by omega n equal to root 2. Okay, now we'll think. So we'll try to solve. So 1 plus, this will be 2 square, that is 4, zeta square into root 2 square is 2, divided by here 1 minus root 2 square is 2, then bracket square plus 2 square, that is 4, sorry, 2 square is 4, zeta square into 2. Okay, now simplify, we will keep numerator as it is. So this denominator will become 1 minus 2 is minus 1, minus 1 square is 1. So 1 plus 4 zeta square 2. So numerator and denominator is same, so the transmissibility will become 1. So when the value of omega by omega n is root 2, then transmissibility is 1. Okay, now read. In the vibration isolation system, if omega by omega is less than root 2, आपण काय घेतलं होतं, here we have considered it is equal to root 2. Okay, so then for all the values of damping factor, see here there is no effect of damping factor when omega by omega is root 2. का effect नहीं है, because directly this total two terms will be cancelled and it will become 1. So for all the values of damping factor, the transmissibility will be, now when this value become less than root 2, then the transmissibility will be greater than 1. ती काय होणार बाळांनो ग्रेटर दॅन 1. ओके अँड व्हेन दिस व्हॅल्यू इज ग्रेटर दॅन √2 then the transmissibility will become less than 1 and when omega by omega n is equal to √2 then the transmissibility will be equal to 1. मी परत रिपीट करतो बघा बाळांनो, ज्या वेळेला ओमेगा बाय ओमेगा एन ची व्हॅल्यू इक्वल टू √2 आहे त्यावेळेला झिटाचा काही इफेक्ट राहत नाही. झिटा किती असू दे ट्रान्समिसिबिलिटी किती होते 1. ज्या वेळेला तुमचा ओमेगा बाय ओमेगा एनचा रेशो √2 पेक्षा कमी होतो त्यावेळेला ट्रान्समिसिबिलिटी काय होते 1 पेक्षा जास्त. आणि ज्या वेळेला तुमचा ओमेगा बाय ओमेगा एनचा रेशो √2 पेक्षा काय असतो जास्त त्यावेळेला तुमची ट्रान्समिसिबिलिटीची व्हॅल्यू काय होत्या लेस दॅन 1. ओके हे लक्षात ठेवा. फक्त एवढं लक्षात ठेवा की वेन ओमेगा बाय ओमेगा एन इज इक्वल टू √2 द ट्रान्समिसिबिलिटी इक्वल टू 1. ओके नाउ द नेक्स्ट just read the statement 11th one. When the frequency of external excitation force is equal to natural frequency of the system. बघा external excitation and natural frequency is same means the resonance will be occurred. So read out the amplitude of vibration is 0, amplitude of vibration is insignificantly small, the amplitude of vibration is very large. Answer is our amplitude of vibration is very large because at the resonance condition the component will increase its amplitude to the maximum. Now next 12th question, just read the statement. The rotating shaft tends to vibrate violently in transverse direction at certain speed and that speed is called critical speed. The critical speed is also called whirling speed. The whirling speed is also called whipping speed. So the answer is all of above. Yes, in rotating shaft when you are going to reach to such speed that it will become resonance. Okay, means it will match with the natural frequency, that is called critical speed. And critical speed is now whirling speed and whipping speed. So all of above is the answer. Now next read 13. The whirling speed of rotating shaft carrying the mass at the center is. बघा the whirling speed म्हणजेच critical speed of rotating shaft carrying a mass at the center is. आता whirling speed is equal to काय असते बाळांनो natural frequency. Okay, so whirling speed means काय critical speed. So when the shaft is rotating with the critical speed means it is going to match with the natural frequency of the system. So more than, less than, equal to natural frequency. Natural frequency जेव्हा match होणार at that case that speed is called critical or whirling speed, means the speed should be equal to natural frequency. Okay, now next 14. बघा for a shaft less than the critical speed the phase difference between the displacement and centrifugal force is. आता हे दोन क्वेश्चन जे आहेत ते तुम्हाला लक्षात ठेवावे लागतील ना. Now if the speed less than critical speed then the phase difference between displacement and centrifugal force is, means we'll have to consider the underdamped system and in that underdamped system we'll have to give the answer for this 14. आणि कोणामधलं विचारलं बघा डिस्प्लेसमेंट अँड सेंट्रिफ्युगल फोर्स. थोडंसं मी वर जातो. डिस्प्लेसमेंट अँड सेंट्रिफ्युगल फोर्स. So for that you will have to remember the displacement and centrifugal force. They are having the angle means phase difference of 0. Okay, याच्याबरोबर तुम्हाला पुढची गोष्ट पण लक्षात ठेवावी लागेल. 15. The question number 15 is for shaft speed more than critical speed the phase difference is 180. म्हणजे ज्या वेळेला they are in phase means the critical speed is less than 1, so the phase difference is 0, means they are in phase. And when the critical speed is more than 1 means more than critical speed, then the phase difference is 180. Now 16th, just read the statement natural frequency of transverse vibration. Okay, So I'll write the formula for natural frequency of transverse vibration. It is 1 divided by 2 pi. The normal formula is root k by m, but the same we can replace by g by delta. Delta is static deflection and g is acceleration due to gravity. And if I put 1 divided by 2 pi, the value of g 9.81 divided by delta, and if I solve root 9.81 divided by 2 pi, then the answer comes out to be 0.4987 divided by root delta. This will be the natural frequency. Okay. Now, natural frequency of transverse vibration is given by, see here they have made one mistake in printing. Actually this value is 0.4987 divided by root delta. Okay, so they have made one mistake here, and the answer is B. But here it is not 4.9, it is 0.4987. If you solve this one, you will get the answer. Okay, so it is 0.4987. Now, just see the next statement. In damped force vibration system, so they have given damped force vibration system, and for that we will have to give the correct statement. Okay, so see, the spring force vector lags behind the displacement force vector by 180. The damping force vector lags behind by displacement by 90. The inertia force vector in phase with the displacement. Yes, all the statements are true. See, force and displacement they are in phase, that is 0. ते आपण वरती पण बघितले. Okay, damping force and displacement they are in 90. Then spring force and displacement they are in 180. Okay, so keep remember these statements. All the statements are true. True means the answer is all above statements are true. And if you remember these three statements, then you can give any answer for the damped force vibration. Okay, now the damping factor zeta is 0. Okay, then frequency ratio omega by omega n is greater than root 2. The transmissibility is, now what will be the value of transmissibility? So I'll write the formula for transmissibility here. It is root 1 minus 2 zeta omega by omega n bracket square divided by 1 minus omega by omega n bracket square whole bracket square minus 2 zeta omega by omega n bracket square. Now they have given the value of zeta is 0. So if this zeta is 0, then the numerator will become root 1 means 1 divided by, now just see the denominator here, it will be 1 minus omega by omega n square bracket square minus the next term is 0. So we don't have here term, so this root will be cancelled with square, and this term will become 1 divided by 1 minus omega by omega n square. So this will be the transmissibility. Okay, so when the zeta is 0, the transmissibility will become 1 minus omega by omega n square. So it is 1 minus omega by omega n square. So the answer is A. Okay, so answer for 18 is A. Now next, the transmissibility is same for all the values of damping factor at frequency omega by omega n. मगाशी बघितलं होतं, when this transmissibility is 1, then there is no effect of zeta, means you can take any value of zeta. म्हणजे झिटाची कुठलीही व्हॅल्यू घ्या, ट्रान्समिसिबिलिटी 1 होणार. कधी? ज्या वेळेला काय आहे, ओमेगा बाय ओमेगा एन इज रूट 2. मीन्स फॉर एनी व्हॅल्यू ऑफ झिटा that is damping factor, the frequency ratio omega by omega n should be root 2, then transmissibility will be equal to 1. म्हणजे ओमेगा बाय ओमेगा एन ची व्हॅल्यू किती पाहिजे? इक्वल टू रूट 2. सो द आन्सर इज सी. सो द ट्रान्समिसिबिलिटी इज सेम, म्हणजे सगळ्या वेळेला सेम राहणार कुठल्या पण झिटाच्या व्हॅल्यूला. कधी ज्यावेळेला ओमेगा बाय ओमेगा एनची किंमत किती असला पाहिजे? रूट 2. काही पण करा, ते एकच येणार उत्तर. ओके, नेक्स्ट द 20, क्वेश्चन नंबर 20. डॅम्पिंग इज बेनिफिशियल ओनली व्हेन. आता डॅम्पिंग कधी बेनिफिशियल होणार बाळांनो? कधी बघा इथे व्हॅल्यूज दिल्यात ओमेगा बाय ओमेगा इन इज इक्वल टू √2 लेस दॅन √2 लेस दॅन 1 इक्वल टू 1. बघा विचार करा डॅम्पिंग बेनिफिशियल कधी असेल when the omega by omega n should be greater than √2. का बघा when it will become greater than √2 then transmissibility will be less than 1. आणि ट्रान्समिसिबिलिटी लेस दॅन म्हणजे 1 म्हणजे काय द फोर्स ट्रान्समिटेड डिवाइड बाय फोर्स इम्प्रेस त्याच्यामध्ये फोर्स ह्या फोर्सची व्हॅल्यू म्हणजे ट्रान्समिटेड फोर्सची व्हॅल्यू काय होणार बाळांनो मिनिमम. So we require in isolation this transmitted force should be minimum. त्या दुसऱ्या सिस्टीमला ट्रान्समिट होणारा फोर्स काय पाहिजे मिनिमम. मग तो कधी होणार when transmissibility is less than 1 and transmissibility less than 1 कधी होते when omega by omega n is greater than 2. Okay, so damping is beneficial only when omega by omega n is greater than 2. Okay, now next 21. For force damped vibration system the vibration isolation is possible. आत्ताच बघितलं बाळांनो व्हायब्रेशन आयसोलेशन इज पॉसिबल कधी असणार बाळांनो when ओमेगा बाय ओमेगा n इज ग्रेटर दॅन √2 तरच आयसोलेट होणार म्हणजेच फोर्स मिनिमम ट्रान्समिट होणार नाहीतर फोर्स मॅक्सिमम ट्रान्समिट झाल्यानंतर आयसोलेशनचा उपयोगच होणार नाही. व्हॉट इज द यूज ऑफ आयसोलेशन विल हॅव टू ट्रान्सफर मिनिमम फोर्स मिनिमम डिस्प्लेसमेंट टू सपोर्ट. ओके नाउ नेक्स्ट रीड आउट दिस 22. In rotating horizontal shaft there are large vibrations when the shafts are rotating at the speed. आता ह्याचं आन्सर बाळांनो जे आहे 22चं हे तुम्हाला लक्षात ठेवावं लागेल when it is rotating with 1/2 of critical speed then there is large vibration of shaft. Okay, next a node means आता नोड म्हणजे काय सांगतो ड्युरिंग द व्हायब्रेशन suppose one mass in vibrating in this direction and other mass in vibrating in this direction means we have two mass system. Suppose this is the system, okay, mass 1 and mass 2. Then there is one point where the displacement is 0 and that point is called a node point. That point is called node point. Okay, now read. A node means section where amplitude of vibration is means displacement of vibration is 0. So it is 0. Now the transmissibility is defined as काय formula transmissibility is transmissibility is nothing but F divided by F naught. Okay, F means force transmitted divided by impressed force. So the ratio of force transmitted through the elastic support to force transmitted through elastic support. No, the ratio of force transmitted elastic support to force transmitted through rigid support, the product, no. So we'll have to read the first two statements carefully. Okay, we'll get answer of 24 here. The ratio of force transmitted, yes, F, through the elastic support to the force transmitted through elastic support. Ratio of force transmitted to elastic support to the force transmitted through rigid support. Yes, this is the answer. Okay, बघा काय आहे there is one rigid support and on that your system is mounted. So this is the system which is mounted. So this is the rigid support which is vibrating with amplitude y. Then this is the displacement of this elastic body with amplitude x. Means force transmitted to elastic body through the support is nothing but the transmissibility. Okay. Now next, the 25 vibrometer is known as low frequency transducer. बघा सुरुवातीला मी सांगितलं होतं in question 5-6 I think that vibrometer they are working with the low frequency. So this one is true. Okay, and accelerometer works with the high frequency. The materials normally used for vibration isolations are see rubber, fork, metallic springs. So all the materials which are having means which will damp the vibrations they are used for the vibration isolation. So rubber, felt, cork, springs they are used for the isolation. So the answer is true. Okay, so see in this session we have solved almost 34 to 35 questions. Okay, just go through these questions. Okay, thank you.